So
Yeah, so
yeah, so this lecture is about system models. Today we'll be discussing about the various elements in the system models and how we can represent that those elements into a model. So as per your syllabi, starting with the first of all the elements of the system models. So a microprocessor switches on a motor. How will the rotation of the motor shaft vary with time? The speed will not immediately assume the full speed value, but will only attain that speed after some time. So that means there is always some lacuna for the system to reach to its peak, whether we are talking about a microprocessor switch or a hydraulic system, which is used to open a valve which allows water into tank to restore the water level to that required, because it will take some time to reach to that particular level. Please switch off your videos. Please switch off your videos. Okay. So, so we'll be starting with first of all the mechanical system building blocks. So in the mechanical building blocks, we have springs, which represents the stiffness of a system, a dashpots, the force opposing the motion, that is a frictional or a damping effects, and masses, the inertia or resistance to the acceleration. So these are the three. Please switch off your mic, please. So there are three systems which you can see on the screen. We have a spring where we will give some force to the system and we will get some output in the form of displacement. Then there is a dashpot system. Dashpot system is that you apply some force on a piston in a piston cylinder, just a representation, and you will get the resistance from the fluid. Okay, so there will be definitely change in position X because of the applied force F, but this change in position X will depend upon how much resistance is being offered by the fluid. The next is the force. Force we have applied on a mass, and once we apply a force on a mass, it will definitely get some acceleration as per the Newton's second law. So basically these three systems are there, which is spring, dashpot, and a mass. And whether we are talking about an electrical system, whether we are talking about a rotational system, we are talking about a fluid system, we are talking about a thermal system, we can represent the analogy of all those systems in terms of spring, dashpot, and mass. This is what our today's topic will be representing everything, like whether it's an electrical system, we'll be representing that in the form of a spring, in a form of a dashpot, or in a form of a mass. So this is the basic idea behind this. For a spring mass system, you already know that the force is proportional to the displacement, and it also depends upon the stiffness of the spring. So as much as high of the stiffness of the spring is, that means you need to apply more force to move the spring to a particular distance. At the same time, if I'm talking about a dashpot system, here, as you know, Newton's law of viscosity holds over there, and here the force is proportional to the velocity. Okay, in the ideal case, the damping or resistive force F is proportional to the velocity V of the piston. So here the force is equal to C times V. And as we know that V is nothing but the rate of change of displacement. So force is equal to C dx by dt. So this is just a representation of the dashpot system, the force which is applied. Now we are coming to the mass, which is a third element in a mechanical system. And this third element is a mass, and here Newton's second law will be hold. So force is equal to mass into acceleration. So mass, acceleration is nothing but the rate of change of velocity. So which is equal to the first derivative of velocity or the second derivative of the displacement. Okay. Now we are talking about the energy stored. As you know that whenever we stretch a spring or accelerate a mass or move a piston in the dashboard, we need a energy. However, in case of spring and mass, we can get the energy back, but with the dashboard, we cannot get that energy. So that means once we apply some force on a system, in case of a dashboard, it moves to some particular distance, but then it cannot comes back on its own because we cannot get the energy back from the dashboard system. This again holds good for the resistance as well, if I'm talking about electrical analogy, because in a resistance you can't get back the energy. Like if I'm talking about electrical analogy, I'm talking about a capacitance. You must be knowing the formula for the energy stored in a capacitance. So but if I'm talking about a resistance, then there is no formula. That means it's not able to means restore its original uh, back to its original position, or we cannot get back the energy dissipated. The same is with the dashboard. So if I'm talking about a spring, definitely there will be some energy stored over there, and that energy is nothing but E is equal to half F square by K. So if I'm talking about a mass, then this energy would be half mb square. So these are the two energies which we can get back. But if I'm talking about the dashboard system, there is no energy stored in the dashboard. It does not return to its original position when there is no force input. So that dashboard, rather than storing it, the power P dissipates depending upon the velocity being given by. So P is equal to CV square, right? So this is nothing but the your rate of doing a work, because rate of doing work is W upon T, and W is nothing but force into displacement, and force was equal to C into V, and displacement upon time is again V. So that's why we will get this formula P is equal to CV square. So this much power is dissipated while we are moving a dashboard system from one point to another point. So that was about your dashboard system. Then comes the rotational system. So rotational system, I'm talking about, we have just discussed the linear systems. So if I'm talking about a rotational system, the only thing is that the displacement X now will be replaced by angular displacement theta, and force is replaced by torque. So everything else would remain same. If you can see through all those equations, our first equation was about force is equal to K into X. But over here now it will be torque is equal to K into theta, because I'm talking about a torsional spring. Then there will be a rotary damper. There was the formula was force is equal to C times V. And over here it would be T is equal to C times omega, because there will be an angular velocity involved over here. And this is equal to nothing but rate of change of angular displacement, which is d theta by dt. Then I'm talking about T is equal to I alpha. That was your third, which was the mass system. So over here, we'll be replacing the mass with the moment of inertia. As we all know that in case of rotational motion, we will consider the mass, moment of inertia. So torque over here is equal to I times alpha. Alpha is the angular acceleration. Now alpha can further be written as d omega by dt, and omega is the rate of change of angular displacement. So it is the first derivative of angular displacement, or the second derivative of the angular uh, first derivative of angular velocity and second derivative of the angular displacement. Again, those laws like energy stored will remains good over here as well. That means the torsional dashboard system will not store any energy. That will hold good over here as well. So if I'm talking about analogy as compared to the linear system, it will be energy stored in the first, that is a torsional spring, will be half T square by K. And while in an angular energy stored by mass rotating with angular velocity omega would be half I omega square. While we are talking about a dashboard system, it will be P is equal to C omega square. Earlier we have driven a formula for P is equal to CV square for a linear system. So now it will be P is equal to C omega square. So this is a table that you must remember, this table, because what we are covering today in this lecture is about the various elements, how they will behave, what will be their equations, and what will be the energy stored in different systems. While we will be coming to the next lecture, where we'll be interacting with the different systems, like we'll be interacting mechanical with the electrical, or mechanical with the torsional, or electrical with the fluid system. Then these formulas which you are seeing right now on your screen will be very useful. So you can directly use these formulas to make a system model for the final equation. Now we can make a building up a mechanical system. So you can take one example for this, like this is spring dashboard mass system over here. So you have a spring dashboard and mass. all the three elements over here, you are applying a force which is needed over here, and you will definitely get some output X. Now, once you apply a force, definitely what you are getting back is force due to spring and force due to dashport. And there is a force F which is acting in the positive X direction, which you can also see in the 17.2a diagram, where you can see that there is a spring, there is a dashport system, and there is a mass involved. Once you are pulling this mass to positive X direction, you are getting a resistance because of the force produced by the spring as well as the dashport system, which is shown over here in the free body diagram as well. Now you can make an equation out of this which is needed. So you can see that force is acting in the positive X direction, and Kx and Cv are the forces produced by spring and the dashport respectively. So we'll be subtracting those forces out of the F, and net force as per Newton's second law would be equal to M into A. So we get the net force F is F minus Kx minus C dx by dt is equal to M d2x by dt 2. That is the second derivative of displacement. So we can rearrange this equation. So this will be M d2x by dt2 plus C dx by dt plus Kx is equal to F. Now this is your differential equation, and you can see that this is a second order differential equation. Once you get this equation, now you will be in a position to model some of the systems which of a mechanical nature, like you have a suspension system attached with a car, which you can see in the diagram 17.3b. Over here there is a mass, there is a spring dashport system, there is a suspension, then there is a tire. So now you can model this. Once you are able to model these systems, then you will be able to make out the final equation. There are bond graphs as well, which I'm just telling you for your knowledge. The bond graphs nowadays are being used to model the systems. Once you are able to make this equation, which is you have just seen over there, which is like this equation. Once you're able to make this equation, you can directly apply bond graphs, and once bond graphs are there, you are able to model the system much in a easier way. Like you want to model the suspension system in a train, then there will be a numerous points where you need to model the system, and so which becomes very easy by using bond graphs. There are very good books available on the bond graphs as well. Okay, so then you can see this is another one. There is a mass, there are two springs are attached over here, and accordingly F will be F minus K1x minus K2x would be there, and net force is M d2x by dt2, and you can make this final equation M d2x by dt2 plus K1 plus K2 into x is equal to F. So this is the how you can model a system, and this is about another directly if you've been studying this mechanical vibration system, this is known as 2 degree of freedom system, which you are rightly now seeing on the screen, which is 17.5 part A. This is known as a 2 degree of freedom system for a vibration purpose. So you are applying a force F on a mass M2. There is a spring K2 which is attached with the mass M1, and M1 is attached to the ground with the spring K1. So the displacement is in the downward direction. It is x3, then x2 is over there, and x1 is at the ground. So accordingly, once you apply a force on a mass M2, definitely you will get some resistance in the upper direction, which is force exerted by the upper spring. So similarly, once you this spring K2 will apply a force on M1, definitely this will get back the force exerted by upper spring, and similarly there will be a force exerted by lower spring. So you can model this equation, this one. So net force will be equal to x2 minus x1, the net displacement on the first mass, and x3 minus x2 is the net displacement on the second mass. So here you can get the net force. So K1 x2 minus x1 minus K2 x3 minus x2 is equal to net force, which is M1 d2 x2 dt. Okay. So this way you can also model the rotational systems. So this is an example of rotational system where this is a analogy as a similar equation which we have directly written over here for the torsional system. That is I d2 theta by dt2 plus C d theta by dt plus K theta is equal to torque. This is just a completely similar equation with a linear system. Only we have replaced the mass with the moment of inertia and x with the angle theta. Okay, so again, we have shown this system like we have shown with a linear system. There is a spring involved, there is a dashboard, and there is a rotational system, which is torque is being exerted on this. So from this equation, we have driven this equation, which is a completely similar equation with the linear system. Now this is another two gear train system, which is you are seeing right now on your screen. There is a torsional system, rotational system. These are the two gears. And then you have applied a torque T. This is a torque which has been applied. And this is a net torque which is now available at this end, which is a T1. This is available at this end. Now there is a torque T2, which is driving another gear, this gear, okay? So this gear is having a moment of inertia I1, angular displacement theta1. This gear has a moment of inertia I2 and angular displacement theta2. So now we can see that if gear 1 is rotated through an angle theta1, then gear 2 will rotate through an angle theta2. So R1 theta1 will be equal to R2 theta2. Okay. So because both are attached with a single shaft, so it will be R1 theta1 is equal to R2 theta2. The ratio of the gear teeth numbers is equal to the ratio n of the gear radii. You must be knowing that, you must have studied in your previous classes. So R1 by R2 is equal to n by n2 is equal to n, which is the gear ratio. If a torque T is applied to the system and torque T1 is applied to the gear 1, then the net torque would be, as you can see over there, we have applied a torque T and we have got the torque T1 over here. So the net torque would be, which is absorbed by the gear 1, which will be equal to T minus T1 is equal to I1 D2, that is the second order of the angular displacement theta. This is nothing but I into alpha, which already we have driven previously. Now for the second gear is getting the torque out of the shaft, and which is available at the second gear, which is equal to T2. And this is nothing but it is equal to I2 D2 theta 2 by dt2. Now we will assume that the power transmitted by gear 1 is equal to that transmitted by gear 2, being on the same shaft. So if the power transmitted is a product of torque and angular velocity, then we can say that T1 is equal to T1 omega 1 is equal to T2 omega 2. Since R2 theta 1 is equal to R2 theta 2, so that means we can also write R1 d theta 1 by dt is equal to R2 d theta 2 by dt. And so if we replace this in the previous equation, we can get that T1 by T2 is equal to R1 by R2 is equal to N. And so once we have driven this relation, T1 by T2 is equal to R1 by R2 is equal to N, we can put this relation in the previous equation, which was T1 minus T2 is equal to T1 minus N T2. N is the number that you have got from here. Okay. So you can see the previous equation. So T minus N times the T2 is what? T2 is the I into alpha. So we have replaced this T2 with the value of I2 D2 theta 2 by dt2. So by rearranging all these things, and you can get some equation out of there, and without the gear. So this is the final equation that you're getting over here. Okay. So if there is no gear, without the gear train, we had simply written that torque is equal to I into alpha. Means there are no two gears involved, only one single gear is there. Then it would have become very easy. We have applied some torque, we have got some acceleration, and this is the Newton's second law, and we can write simply torque is equal to I1 d2 theta 1 by dt2. Okay. Okay. So only 11 students have joined out of a class of 40. Okay. The basic building blocks of electrical systems are inductors, capacitors, and resistance. Now we are into a electrical system analogy. Okay. Again, our concern is about the spring system, the dashboard system, and what? The third one was the mass system. Okay. So now we have analogy. We need to make it for the electrical system building blocks. So we have first the inductor. Inductor is the, you must be remembering from your 10+2 class. For an inductor, the potential difference, okay, V is the potential difference across it and any instant on the rate of change of the current through it. It is equal to V is equal to L di by dt. You must be remembering this relation from your 10+2 class. That was there, where L is the inductance. The direction of the potential difference is in the opposite direction to the potential difference used to drive the current, which is also known as a back EMF. You must be remembering the Faraday's law, right? for the back EMF. The equation can be rearranged to give you, this is the same equation, this equation. We have taken integration and we have taken all the terms on the left side. So I becomes equal to 1 by L integration of potential difference with the time. Either you can use this equation depending upon your problem. You can also use this equation. You must remember these two elements and their representation, because while you will be making a system model, you must be knowing that. Ultimately, we also will be getting one table for this as well. Now, the next element would be the capacitor. The potential difference across it depends upon the charge on the capacitor plates at the instant. You must be remembering that V is equal to Q by C. I hope you remember from your 10+2 class, where C is the capacitance. Since the current I to or from the capacitor is the rate at which the charge moves to or from the capacitor plates. So I is equal to nothing but rate of change of rate of flow of charge. So it is equal to dq by dt. Then the total charge Q on the plates would be integration of I times dt. And so by replacing the Q in the previous equation, which was V is equal to Q by C. So over here we have replaced Q with the integration of I with the dt. We have got potential difference formula as 1 by C integration of I times dt. So this is the capacitor. And for the previous inductor, what was I? It was 1 by L integration of V times the time. Over here we have got the potential as 1 by C integration of I times dt. So we also know that V is equal to Q by C. We can take the differentiation. dV by dt is equal to 1 by C dQ by dt, and dQ by dt is nothing but the current. So dV by dt is equal to 1 by C times I, and I is equal to C times dV by dt. So this is another representation for the capacitor. So you have the representation for the capacitor, for the inductance. Now we have got the resistance, which is much easier to deal with. V is equal to R times I. Now, as I told you in the linear mass system, which was the mechanical system, I told you spring stores the energy, your mass stores energy, but dashpot is not able to store the energy. The same thing is over here. Your capacitor will store the energy, your inductor will store the energy, but your resistance will not be able to store the energy. And the formulas for the energy stored in inductor would be E is equal to 1 by 2 Li square. You must be remembering this energy equation from your previous classes, and E is equal to half CV square. This is the energy stored in a capacitor. And as we have found in the case of a spring mass system, we have found out that dashpot system where the power is dissipated was equal to CV square. Over here, the power dissipated in the resistance is the nothing but current into voltage, and current is nothing but V by R. So in that case, P, that is a power dissipated through resistance, would be V square upon R. Okay, so now we have the building blocks ready for the electrical analogy. So this is inductor, and these are the two formulas for the inductor, and this is energy stored in the capacitor, inductor. And then this is the formula for your capacitor. This is the energy stored in the capacitor. Then this is the resistance, and this is the power dissipated along the resistance. Okay, so these are the analogy. Now we can also, like we have built a model for the mechanical system, we can also build a model for an electrical system. The equation describing how the electrical building blocks can be combined are Kirchhoff's law. Okay, so again, you must study one or two first two chapters of 10+2. And there was a chapter on power electronics in the 10+2, which was about energy dissipated inductor, capacitor, RLC circuits, LC circuit. Those are very, very important. Even today's scenario, we are working on a project on a hybrid machine, and there we are again applying the RLC systems. So those chapters are very, very important. So we are also using the formulas from those chapters over here. I think this is the second chapter in the 10+2 where we have used the Kirchhoff's law. And in a Kirchhoff law 1, the total current flowing towards a junction is equal to the total current flowing from that junction, means the algebraic sum of the currents at the junction is 0. You must be remembering that. Then there's a law 2, in a closed circuit or a loop, the algebraic sum of the potential differences across each part of the circuit is equal to the applied EMF. Okay. So these are the two laws which we'll be using for building up a model from the blocks. Now consider a simple electrical system which is shown in a figure 17.9. There you can see that we have applied a voltage V, and the current is being fed to the resistor, which is connected with the capacitor in a series. Now consider applying a Kirchhoff's second law, this voltage must be equal to what? The voltage dissipated across resistance and the voltage available across the capacitance. So V is equal to VR plus VC. Okay. So where VR is the potential difference across the resistor, and VC that across the capacitor. Now, since this is just a single loop, the current I so now consider a simple electrical system. Okay, I was here. So where VR is the potential difference across the resistor. I told you this as well. If the output from the circuit is the potential difference across the capacitor. Now what we are doing is we are taking the output across the capacitor. We are giving the input over here at the applied voltage. So if the output from the circuit is the potential difference across the capacitor, then since VR is equal to IR and I is equal to C dVC by dt, this already we have proved from the previous formula, previous page. So V is equal to RC dVC by dt plus VC. This is nothing but very easy like. So this is the total potential available across the circuit. This gives the relationship between the output VC and input V and is a first order differential equation. This one is a first order differential equation. I think you must be, able to understand, because VR is equal to IR and we have replaced I with this formula C dVC by, which we have earlier driven. Okay. So we have replaced this formula over here and this is the total voltage available. This is a first order differential equation. Now we have included one more block over here, which is we have applied voltage. It is passing through a resistance, then inductor, then capacitor. Okay. So where VR is the potential difference across the resistor, VL that across the inductor, and VC that across the capacitor. Since there is just a single loop, the current I will be the same through all the circuit elements. That's a basic, obvious thing. If the output from the circuit is the potential difference across the capacitor, again we are taking the output from the capacitor. Then since VR is equal to IR, VL is equal to I by dt, so we have replaced the VR and VL from here over here. That is VR is equal to IR and VL is equal to LDI by dt, and VC is the output which we are getting. Again we are using that I is equal to C dVC by dt, and so we have replaced I over here. So and we have taken the second order difference, we have taken the differentiation of this formula as well. So finally this is what we have got. V is equal to RC dVC by dt plus LCD, second differentiation of the voltage available at the capacitor, and this is the voltage available at the capacitor. So we have completely means formulate the equation in terms of the output voltage available at the capacitor. This is a second order differential equation. Okay. Similarly, there are two more means systems which you can see on the book. If you have any doubt, you can ask me in the next lecture. This is what is available. Like you can take this figure 17.12. Okay. So by using Kirchhoff's first law, you have a current I at this node. I1 is coming, I2 and I3 are exiting from this node. So as per Kirchhoff's law, I1 is equal to I2 plus I3. Now I1 is what? Potential difference from A to the applied voltage, V minus VA upon the resistance. And I2 is the current which is available over here, which is the 1 by L integration of VA into dt, which was there on the capacitor. And I3, which is passing through inductor, would be C dV by dt. All these block elements have already been shown in the previous table. So we have used this and replaced the I1, I2, I3 in this above equation. So finally, this is what we are getting. This is the final equation in terms of the output voltage VC. So you can use these analogies. Now over here it is nothing but compared the two systems between mechanical and electrical. I already told you. So the current is being analogous to the force, because current is a driven thing in an electrical system, which is driving all the means potential or anything, then the potential difference is analogous to the velocity. You apply current, you get some potential difference, and the dashboard constant C to the reciprocal of the resistance. So these are the complete analogy as compared to the mechanical system. These analogies between current and force, potential difference and velocity hold for other building blocks, with the spring being analogous to the inductance and mass to the capacitance. Spring analogous to the inductance and mass to the capacitor. You must remember these things. So you already have driven this equation, m d2x by dt2 plus c dx by dt plus kx is equal to f. This was the equation driven in the first mechanical setup, and this is the equation with the electrical system. So these are the two analogies that you have seen over here as well. Okay. Now the time remaining is only 3 minutes. Now I throw open to you. You can ask a few of your questions, because right now you are at home and you must have some queries regarding the mechatronics. So for these 3 minutes, you can open your mic and you can interact with me.